Hello. Let's see. Well, I just saw your message, Madison. Let's see. Let me check my schedule really quick so we could schedule the session tomorrow. Let's see.
Sounds good.
Hmm. Let's see. Tomorrow, you are free 10 a.m. to 3 p.m. And then 5 to any time. Okay. Do you want to do 5 to 6 tomorrow, Madison?
Yeah, it's perfect.
Okay, let's do that. Let me schedule that in. And you guys have quizzes this week, right? I think for 8B and 118A, Kelly. Later you have your final next Friday, so that's good. Is there any topics you guys wanted to go over? Anything you guys wanted to go start with? Let's see. Save. Okay. Share screen. Yeah, I just had 2 exams today. It was it was crazy. I studied like the morning of and then I got 95 on both of them. So I'm happy about that.
Gosh.
It was a lab
Congrats.
practical. It wasn't like a lecture like exam. It was more like lab practical, like a physical lab like test. So it's more like practice repetition. So it's not like a lot of like concept heavy stuff. It's like more like physical procedures, Yeah.
That's so good.
Yeah, but I
Especially
was so
the
stressed.
morning of.
I know. I was like really stressed this morning, but now like I'm so happy. Like when I went home, I took a big fat nap.
Oh, well
Yeah, so
deserved. Very well
yes.
deserved.
Yes, of course, of course. So, um, yes, thank you. Let's do 8B and 118A because you guys have the quiz this week, and then 118B after. So, Madison, is there anything you wanted to go over today? Any practice rounds, any topics you wanted to go over?
I was wondering if we can. I know we were working on that one mechanism last session. Like that kind of applies to multiple different reactions. Let's see.
Wait, let me check
I just
our
have.
notes really quick. Yeah. Did
I'm
you get
not
home
very
from
prepared.
campus or
Yeah, I had a
um
midterm for a different class.
oh
Till 8. So,
oh my God, how did that go?
we'll see. But better than the first one, so
Yeah. What
I'm
class was
optimistic.
yeah. What
It
class was it
was
for?
what class?
Mm-hmm.
It's a farmland resource appraisal class.
Farmland research appraisal class. I see.
Interesting stuff.
Yeah. That's good.
Um, the reaction was, I think it was for like nucleophilic acyl substitution
Yes.
and like the Fischer esterification.
Yes. Nucleophilic acyl substitution. So for that one, we went over the reactivity of the different carboxylic acid derivatives, right? Like the acyl halide, the carboxylic acid, the ester, and the amides, and the two factors that rank the reactivity. Like the first factor is leaving group ability, and the second factor is carbon electrophilicity. Right, where like
Oh.
if we have this azo halide right here, that's the most reactive derivative. And then after that, it's the carboxylic acid. And then after that, it's going to be the ester. And then after that, it's going to be the amide. But keep in mind that this amide right here can be like NR2. It could be NRH, right? It doesn't have to be NH2. The reason why the reactivity increases from right to left here is because the leaving group is like better from left to right as well. I mean, right to left as well, right? The pink circles here are the leaving groups that I just circled, right? When they leave, they would leave with a -1 charge. So X here is the most stable leaving group because when it leaves with a negative charge, it's the most stable because it's the most electronegative atom. OH minus or minus, the negative charges on the oxygens are more stable than the negative charge on the nitrogen because oxygen is more electronegative than nitrogen. Right, now the other factor that describes the electrophilicity, I mean the reactivity, is the electrophilicity of the carbene-carbon. How positively charged the carbene-carbon is. The azo halide carbene-carbon, it has the biggest positive charge because it's attached to the carbene-carbon and it's not gaining as much electrons as it is, right? Because this halogen here, because it's very electronegative and it has a poor peer orbital overlap, it cannot do resonance very well with this carbonyl right here. And because of that, this carbon here is not gaining electrons as much. So it's going to remain positively charged. Whereas if we look at the other extreme, this nitrogen right here, it's the least electronegative atom compared to oxygen and halogen, right? And because it's the least electronegative atom, it's the most willing to share its electrons and donate electrons into the carbon, neocarbon. And because this carbon is gaining more electrons, gaining more negative charge, its positive charge shrinks a lot more, right? It's becoming more neutral. And that is going to make it less reactive now because the positive charge is so small, it's so stable, it doesn't want to react anymore, right? Oxygen is in the middle. It's less electronegative than the halogen, but more electronegative than the nitrogen. Okay. Now, we can go over like a lot of these nucleophilic azo substitution reactions where the azo halide here can create any of these lower reactive derivatives in one single step. This carboxylic acid can create the ester and amide in one single step. The ester can create the amide in one single step in nucleophilic azo substitution, right? Now let's talk about the azo halide reactions. Because the azo halide is the most reactive derivative, it does not require acid or base catalyst, right? It just needs neutral conditions. So I'm just gonna draw out the reagents required to convert this azo halide to each of these other carboxylic acid derivatives here. Okay. We just need water, neutral water, to convert an azo halide to the carboxylic acid here because we're substituting this halogen with the OH right there. And the OH here comes from the water. If you want to create the ester from the azo halide, you want to use an alcohol where the OR group of the alcohol is going to be the OR group of the ester. And notice the pattern here. We're taking away one hydrogen when we do this.
Can you do the alcohol to the OR group with just our OH?
Like this carboxylic acid to this OR group right here?
Yeah. Sorry. Yeah, it's not alcohol.
We can create the carboxylic acid to the ester, but it's not going to be H2O. Okay. Right, it's going to be different conditions, and that's the Fischer esterification conditions. Okay. Right, that like if we go from carboxylic acid to ester, that's going to be the R prime OH, the alcohol, like the OR of the alcohol, and H2SO4, strong acid. Okay. This reaction here can never happen in basic conditions because in basic conditions, this carboxylic acid here will get deprotonated, right? Because acid-base reactions are one of the fastest reactions you have in OChem.
Right.
So you cannot do R prime O minus and its solvent R prime OH, right? Because this strong base here, the R prime O minus, is just gonna deprotonate the carboxylic acid to give you this carboxylate here. And I know Levens for sure can put this on the predicted product to trick you guys, right? Because a lot of people would try to substitute that R prime O minus with the OH to create this ester right here in basic conditions, right? But that does not happen. We do not get that in basic conditions. We get this deprotonated carboxylic acid here, the carboxylate instead.
Okay, perfect.
Right? Yes. Now, if you want to create an amide from the carboxylic acid, then you're going to use neutral amine. And in this case, you need at least 2 equivalent to do so. And you can find the mechanism, like the second equivalent is needed to deprotonate the final step to get to this neutral product here, right? But you need at least 2 equivalents of the amine to convert an acyl halide to the amide.
Okay.
Right. Now, let's move on to the carboxylic acid reactions. The carboxylic acid, we just talked about one of them, Fischer esterification. We can convert that to the ester by using alcohol and strong acid. We can convert the carboxylic acid to the acyl halide, but not through nucleophilic acyl substitution, because we just said that nucleophilic acyl substitution will allow any of these more reactive derivatives to create any of the lower reactive derivatives in one step, right?
Right.
The acyl halide is more reactive than the carboxylic acid. So this carboxylic acid turning into this acyl halide here is not gonna like go through in nucleophilic acyl substitution. It's just gonna go through an SOCO2 reaction, right? And that's not gonna go through a nucleophilic acyl substitution reaction. Just recognize this reagent for sure. SOCO2 will convert the carboxylic acid to acyl chloride.
Right.
Okay. Right. Now the amide right here is going. It can be created from the carboxylic acid using NH3 dilute H2SO4, but I don't think she really went over that reaction. Right? Because if you have excess H2SO4, that's gonna shut down the reaction.
I don't think so.
Yeah, did she go over carboxylic acid reaction to convert to an amide? Because like if we have like excess H2SO4, that's gonna protonate the NH3 instead, because NH3 is a stronger base, and that's gonna create NH4 plus. I don't think she went over this reaction, but I'll let you know. So I don't think you have to worry about converting carboxylic acid to the amide, because the better way to do that is to go from an acyl chloride.
Okay.
Right. Now let's move on to the ester reactions. The ester can create an amide in one step by doing NH3 heat and catalytic acid, and that acid can be like H2SO4 or HCl, right? It could have also been in basic conditions as well, like NH2 minus and its solvent NH3 with heat. So this can happen in acidic or basic conditions, but heat is required here. And the reason why we require heat is because the ester is one of the lower reactive derivatives.
Okay. So it needs something to like induce the reaction.
Yes, to induce the reaction, correct. To add more energy to the system and induce the reaction, right? The ester here like can go back to the carboxylic acid. Think of the carboxylic acid as the parent functional group. Like any of these derivatives can go back to the default, which is the carboxylic acid right here.
Okay.
Right, and to do that, those reactions are hydrolysis. So to convert a ester to the carboxylic acid, we're going to use water and H2SO4, right? If, however, you use basic conditions like NaOH, H2O, you're not going to get the neutral carboxylic acid, you're going to get the carboxylate, right? Because we're in basic conditions. So that basic conditions is going to deprotonate the carboxylic acid to the carboxylate right there. This specific reaction is called saponification. This creates soap, So this is like a vocab question right here for leavens. Just a quantification. Right? Because this R group right here is the hydrophobic region of the soap, right? That attracts the oil and dirt.
Oh, yes. Okay.
Right? And then this is the
Right.
hydrophilic part, which like attracts the water when you wash things with
Yeah.
water and soap. Right. Now let's move on to the amide reactions. Amide can't really do a lot of things, right? Because amide is the least reactive derivative, but what it can do is that it can go back into the parent functional group, right? It could reset to the default by doing hydrolysis with H2O, H2SO4, and heat. And heat is required here because amide here is the least reactive derivative right there.
So, okay.
And this is hydrolysis right here because it's going back to the parent function group, carboxylic acid.
Okay.
Right. And all hydrolysis reactions will have water to it. Right.
So the
but notice how
that were H2O and H2SO4?
Yeah.
Together, right?
Yes, together.
Okay.
But the lower reactive derivatives here require this H2SO4 because they need that catalyst to get started with the reaction.
Right.
Because they're not reactive. But if you look at the acyl chloride here, we did not need acid at all, or we did not need heat at all. We just needed a neutral water and it went through.
Right.
Because this is the most reactive derivative, it reacts with a neutral water molecule like that.
Got it.
Yes. Those like the nucleophilic acyl substitution reactions, I recommend practicing the mechanism because it's the same exact mechanism, just different nucleophiles, right?
Right.
And also there's two other sets of reactions for these carboxylic acid derivatives: organometallic reactions and reduction reactions. And the reagents that you're gonna see for that is that for organometallic, you're either gonna see R MgBr, second step H3O plus, or you're gonna see RLi, second step H3O plus. They're gonna do the same thing though. For reduction, you're gonna see first step for Leibniz class, like for 8B, I've only seen her give LiAlH4, second step H3O plus. Right. So I think we went over this.
Yes.
Yeah, we went over the reduction for sure. Yes. Okay. I will go over organometallics later, if we have time, but practice these here. Let me give you a problem to work on, so then I could check on it after.
Okay, those are good. That like little like diagram is good to put on the note card.
I just kind of like BS'd it. Like it's kind of like like all over the place. It could definitely be cleaner for sure.
Yeah, but if you reorganize it would be really helpful.
Yes.
Correct? Okay.
Yes, correct. It could organize all the nucleophilic acyl substitution and interconversion between the derivatives for sure.
Okay.
Right. Okay. Now let's give you two problems here. Let's give you intramolecular reactions as well, which is gonna. I think Jenna could also try these as well. Let's try. Predict the product here and draw the mechanism.
And the mechanism is it's nucleophilic acyl substitution.
Yes, nucleophilic acyl substitution.
Okay.
And okay, these two here, I want you to predict the product and draw the mechanism. Madison and Jenna. Okay. Hey Layla, did you have a question or topic you want us to go over for 118B? Any practice problems you want us to go over? Sent the two mechs. Okay, let me see. Oh, I see it. Okay. Halogenation of enols and enolates. And alpha carbons are acidic. Okay, yeah. So did Helix go over the mechanism of these in class? Like the halogenation of enols and enolates?
Let me double check.
Okay, okay.
Yeah, I see them, I think. Or
Mm-hmm.
he kind of just like wrote the product.
He just wrote the product. He didn't draw out the mechanism.
Yeah.
Okay. Let me show you what the mechanism is like and how to understand it conceptually for this here. So the reaction that he gave was one equivalent of Br2, CH3, CO2H, and that's gonna alpha brominate this carbonyl right here. And it's gonna stop at one equivalent. Right. This is the carbonyl carbon. This is the alpha carbon, the first carbon away from the carbonyl carbon. And we see that in this reaction, we added one bromine to the alpha carbon from this reagents, one equivalent of Br2 and CH3CO2H. This CH3CO2H is acetic acid. Right here, this carboxylic acid, right there, CH3CO2H. So we're in acidic conditions here. The mechanism is like this. Because with acidic conditions, we're gonna protonate the carbonyl oxygen. That's the most basic atom we have in this molecule. So we're gonna use that carbonyl oxygen to deprotonate this carboxylic acid to give me this protonated and activated carbonyl right there. Once you have this protonated and activated carbonyl right there, we can then use, let's see here. Let's see, what is the deal here? I'm gonna try something and I'll double check with the mechanism after, but let me see if this works. Create an enol. Once I create that enol, my nucleophile is this alpha carbon, which I'm gonna star. And then once that is that, I'm gonna bring in my Br2, reform my carbonyl, have this alpha carbon attack the bromine, kick out the other bromine, create this intermediate with the carbonyl positive charge, bromine right there. And then at this point right here, we're gonna we could use Br minus that got kicked out to deprotonate the carboxylic acid to go back to this final product right here. So we stop here. We don't keep going. Let me try out the mechanism for the basic conditions and see why we get over alkylation of it in basic conditions, because we see that the second reaction here, we have the same ketone, but this time we have excess Br2 in basic conditions, NaOH. This NaOH here is gonna deprotonate the most acidic hydrogen, which is this alpha hydrogen here, and create this enolate ion, where I'm gonna explain this after, but let me just try to do this to see if it makes sense for me, and then I'll explain after, just in case it doesn't work out later. Reform carbonyl, attack the bromine, kick out the other bromine, get that carbonyl right there, and have this bromine right here. Now once we get to this form right here, this reacts faster because I see what's going on here now. Okay. Yeah. So another hydrogen here is gonna get deprotonated by another base. Deprotonate that. So there's a very sneaky conceptual thing going on behind the scenes here. Right. And another Br minus is gonna come back. Alpha carbon attacks that, kicks that out there, put that there, and give us this final product right here where we get 2 bromines on this alpha carbon. We basically substituted all of the alpha hydrogens on this carbon to the bromines right there. Okay, let me explain what happened here. So halogenation of the enols and enolates. When you have a ketone, like this, right? And you react it with X2 in acidic conditions. So this is acidic conditions right here. You do mono halogenation. Only halogenate the alpha carbon one time. This is the alpha carbon. We only added one of the halogens here one time because this is in acidic conditions. Here's the mechanism. Because we have strong acid, we're gonna look for the most basic atom. The most basic atom here is this carbonyl oxygen, which is gonna get protonated by the strong acid to give us this protonated carbonyl right here. Once we have that protonated carbonyl, then the conjugate base here is going to deprotonate the alpha hydrogen to create this enol right here. Now, once we have this enol right here, a lot of people think that this oxygen here is the nucleophile, right? But it's not the nucleophile. It's actually this alpha carbon. And the reason why is because if I draw you out the resonance structure of this enol, we see that the alpha carbon here of the double bond has the full negative charge, right? And because it has the full negative charge right there, it is less stable than the oxygen, making it more reactive, more nucleophilic. That's why this alpha carbon here is the nucleophile. So when we go to reform the carbon double bond oxygen, the carbonyl right there, we're gonna break the octet rule for this carbon. So to conserve the octet rule, we know that this double bond here has to go onto that carbon, giving that carbon a negative charge. But instead of drawing out the whole resonance structure, I just drew out that negative charge attacking the bromine, kicking out the other bromine right there. To make it more clear, right, I could highlight this double bond right there. That double bond made this new bond between the carbon and bromine right here, right? Between this starred carbon and bromine right there. That's where the bond came from that double bond right there. And then the last step here was that the Br minus deprotonated the carbonyl oxygen to get to this final answer. Before we move on, do you have any questions about the mechanism, Layla, and why things happened, like at a certain step?
Could you just double explain why the double bond goes there again?
The
Like
double
add the
bond,
bromine?
oh, like why the double bond, like this double bond right here?
Yeah.
Yes. We created this double bond from deprotonating this alpha hydrogen right here. So this base that we created earlier from the carboxylic acid deprotonates this alpha carbon. It grabs that hydrogen right there, right? And as a result, it forms this carboxylic acid again, right? Because this blue hydrogen here is that blue hydrogen right there. But when that blue hydrogen is grabbed, the bond between the blue hydrogen we grabbed and carbon right there, it shifts over to create a double bond right there, right? So this yellow bond right here became that double bond right there. But we had to do something here because when we create a double bond between this carbon and this carbon would break the octet rule. It would have way too many bonds. It has 5 bonds right now. So we have to pop the double bond onto the oxygen, giving that oxygen a pair of electrons, right? And that is going to be a single bond OH. And because it gained a pair of electrons, it is now neutral. So that's where the double bond came from, right? And this right here is what we call an enol, an alkene next to an alcohol.
Okay, got it. Thank you.
Yes. And when you have an enol, right, your nucleophile is going to be the alpha carbon. this is your nucleophile right here. Now, from that point, we attack the bromine, kick out the bromine to create this new bond right here, and then the Br minus deprotonated the carbonyl to get us our final answer, the monohalogenated product right there. Now, for the next one right here in basic conditions, this strong base here is gonna deprotonate the alpha carbon to create the enolate ion. This right here is the enolate ion because this is a deprotonated enol. Right, let me switch my Wi-Fi really quick. I think it's lagging really. Okay. So this enolate ion here, let's do the same thing. If I draw out the resonance structure like that, I would get a full negative charge on this alpha carbon right there. And that's why this alpha carbon here is my nucleophile, my star. So when I go back down to reform the carbonyl, I use this alpha carbon to attack the bromine, kick out the other bromine to give me this intermediate right here. Right, and because I have a strong base, I'm gonna deprotonate this other alpha hydrogen right here to create another enolate ion, and that does the whole process over again. Once of the enolate ion, we attack a second equivalent of Br2 to create that polyhalogenated structure, right? So basic conditions, you halogenate the alpha carbon multiple times. Polyhalogenation. Right. So what Helix put on his lecture slides is that, like, because this oxygen here is positively charged, right? This oxygen here is gonna like want to withdraw electrons a lot to make it stable. And because of that, the hydrogen here is going to have a small partial positive charge. Due to this positively charged oxygen in acidic conditions here, withdrawing electrons from that hydrogen. So this is the sneaky concept I'm talking about here, right? And because of that, this hydrogen here has a small positive charge, which is not very acidic anymore. So that's why we can no longer deprotonate this hydrogen right here, right? It's also stabilized by this electronegative atom bromine right here, withdrawing electrons from that hydrogen right there. Whereas if you look at this intermediate right here, the pink hydrogen right here has a bigger positive charge than the previous one I just drew out. Because this carbonyl oxygen here is not positively charged, so it's not angry. It's not going to withdraw electrons as much as it did with a positive charge like that, right? And because this has a bigger positive charge, this is more reactive. It's more acidic. So that's why another base is able to deprotonate it, making another enolate ion, attacking another halogen, like that. So that was the sneaky concept there, right? The sneaky concept was that we have another acidic hydrogen to deprotonate to create another nucleophilic enolate ion in basic conditions, right? But in acidic conditions right here, this hydrogen is not acidic anymore, right? So that's not as reactive. So we stop at the monohalogenated products here. We only halogenate the product one time. Any questions on that concept, on why in basic conditions we are able to halogenate the alpha carbon multiple times, but in acidic conditions we are only able to do it one time?
So it's just basically because of the H.
Yes, at this intermediate right here, the H of the basic conditions is still reactive enough to get deprotonated to create another enolate ion, which can attack another bromine. Whereas in acidic conditions, the H in this intermediate right here is not acidic enough anymore. So we stop at that reaction, at that product.
Oh, okay, that makes so much more sense. Thank you so much.
Yes, of course, of course. This is more for predicted product, I would say. Like if you see a ketone and you see X2 in acid, just know that you're gonna add one halogen to the alpha carbon. Whereas if you see a ketone and you see excess X2 with basic conditions, just know that you're gonna add like a lot of halogens to the alpha carbon as much as you can. Because this alpha carbon here has 2 alpha hydrogens, you're gonna substitute all 2 alpha hydrogens with the 2 halogens you have, right? I remember one question that Helix put, it was something like this. He had this acetone here, and he had excess Br2 in basic conditions, and the answer was this right here. Right? Because this is the carbonyl carbon, this is the alpha carbon, and this alpha carbon here has 3 alpha hydrogens. So we're substituting all 3 alpha hydrogens with the halogens that we have, right? In the previous case, we only had 2 alpha hydrogens. That's why we had 2 bromines. But in this case, we have 3 alpha hydrogens, so that's why we have 3 bromines in the product in basic conditions. If you, however, had the X2 in acidic conditions, which is the CH3CO2H or H2SO4, any acid here, you're only gonna halogenate the alpha carbon one time. So that would be the answer for acidic conditions, right? You're only gonna add one halogen to the alpha carbon like that. So that's what you would most likely see this reaction in the exam.
Okay, thank you so much.
Yeah, of course. Just in case it shows up an explanation problem, right? I gave you the sneaky concept just in case. It shows like why in acidic conditions it stops at one halogenation, whereas in basic conditions it's able to do polyhalogenation, add it multiple times. And the reason is what I gave you earlier. So that's good for explanation right there. Right. Okay. The other thing that you sent me to go over for 1SNB was alpha carbons are acidic. So we can have irreversible deprotonation with LDA. And LDA looks like the structure right here, which he drew out. Right? And he also gave negative 78 degrees Celsius. This LDA here is a very strong base. Very strong. Very strong, bulky base. Bulky base. So when you have an asymmetrical ketone like this reacting with LDA, and I'm going to draw out the structure of LDA like that, in negative 78 degrees Celsius, this is going to result in a kinetic product, the fastest formed product that we can do, right? Because this is very bulky and we're in low conditions here. So the fastest formed product is going to be the hydrogen that's the easiest to grab, the most available hydrogen. This right here, the less substituted hydrogen, is the most available hydrogen. So that's why we're going to deprotonate that hydrogen, create a double bond right there, pop the double bond onto the oxygen to create this enolate ion right here, right? And this is our kinetic enolate, right? And we stop here. We cannot go backwards. This is irreversible. It's irreversible because we used a very strong base in low temperature, LDA, right? But keep in mind here, the O- is not your nucleophile. This alpha carbon right here is the nucleophile, not this alpha carbon because there's no double bond right there. So when you put some kind of electrophile nearby or an acid nearby, the carbonyl is going to reform, and you're going to use the alpha carbon right here that I just starred to attack the electrophile or the acid, hydrogen right there, right? And that's going to be like the other reactions like alkylation or acid reaction, right? But now let's talk about reversible deprotonation leading to the thermodynamic product. So let's use the same asymmetrical ketone, and this time we use another bulky base, turbotoxide, right? This is also a strong bulky base, but it is weaker than LDA. And the reason why it's weaker than LDA is because LDA has a nitrogen atom. And we said earlier that nitrogen is less electronegative than oxygen, so it's more willing to donate electrons and attack. So that's why it's a stronger base. Because oxygen is more electronegative than nitrogen, it doesn't really want to share its electrons. It doesn't really want to attack. So it wants to keep its electrons more, making it a weaker base than LDA. So that's why this is going to be a reversible base, because the first thing that would happen, right, is that the bulky base here will grab the less substituted hydrogen first because it's bulky, create that kinetic enolate to begin with, right? But because this is reversible, we're going to go backward here, right? We're going to reform the carbonyl and have this alpha carbon here get protonated by, let's say, tert-butanol to reform our turbotoxide and our asymmetrical ketone again. Because this is reversible, right? Like, it is possible, but this is low yield here. The turbotoxide will grab the more substituted hydrogen to create the more stable enolate ion, more stable alkene, right? So this right here that I just created is called the thermodynamic enolate, aka the more stable product, the more stable enolate, the more substituted alkene right there. This is in very low yield. As we can see in this arrow, like that is not going to be very favored. Especially because this is a carbonyl, this is the enolate right here. But using turbotoxide, we're able to get the more stable enolate, right? So if you use LDA, your enolate is going to be at the less sub-alkene. If you use turbotoxide, your enolate is going to be the more sub-alkene. And that's more for predicted product problems, right? So using that, I'm going to give you an example problem here. Let's say I have something like this, and I give you two reagents. The first reagent, LDA, negative 78 degrees Celsius. Second step is going to be this haloalkane. The second reaction is going to be turbotoxide with tert-butanol as the solvent. And the second step is going to be this reagent right here. Okay? Practice predicting the product for these reactions, and I'll go back to check your answers, Layla and Masna, for 118B. Any questions about this, Layla or Masna, that I just went over for 118B before I move on to 118A? Okay, so let's move on to 118A. Kelly, you had two questions. When do hydride or alkyl shifts occur, and what reagents? Solvents commonly used to result what products like PCC, PBr3, Jones, etc. It is this time. Can we go through a synthesis problem? Okay, so hydride or alkyl shifts are known as carbocation rearrangement steps, or simply just rearrangement. And they happen when you come from a less stable, aka, or no, actually not, because don't associate like stability with substitution all the time, because in 118B you're going to learn about allylic, like resonance carbocations, right? But for 118A, you could think about less stable is less substituted, more stable is more substituted carbocation. So basically, you're converting a less stable carbocation to a more stable carbocation in these shifts. Less stable carbocation to more stable carbocation. Did your professor go over concerted shifts, like concerted hydride shift or concerted alkyl shift, or just regular shifts, regular hydride shift, regular alkyl shift? right? And these are the carbocations here. This is a methyl carbocation. This is a primary carbocation, secondary, tertiary carbocation. Stability increases from left to right here, which is due to hyperconjugation. It has more friends. The carbocation has more friends, more groups around it. She mentioned concerted, but you don't quite understand. Okay, so whenever you form a carbocation intermediate, right, which multiple mechanisms can form a carbocation. SN1, E1, alcohol with HX reaction that we did last night. And when you get to 1SNB, there's going to be a lot of carbocation intermediates for alkenes as well. You always have to stop and see if you could convert that carbocation to a more stable position. We see that we have a secondary carbocation here in this structure. We stop and we look at the left and right to it and see if it can become any more stable, which is gonna be the right side. But we do not move the carbocation like that, because when we draw arrows, the arrows show the movement of electrons. There's no electrons in this carbocation, 0 electrons there. What we gotta do is we gotta draw out that invisible hydrogen with the invisible bond to shift that whole bond and hydrogen over. That's called a hydride shift. And because this carbon here had 4 bonds, 1, 2, 3, 4, and it lost the bond, it only has 3 bonds now, it has a positive charge. And because the carbon that had a positive charge gained a bond, it's now neutral. Right, because it always had that invisible hydrogen right there, so now it has a second hydrogen, making it neutral with 4 bonds. So we came from a secondary carbocation to a tertiary carbocation, and that's the point of the hydride and alkyl shift. That's when you do that, to convert a less stable carbocation to a more stable carbocation. Any questions on that, Kelly? On like why we do that shift? No. Okay, so let me show you the concerted shift now. Let's say you had an SN1 reaction with that halocane and water. Well, let's do ethanol. Like, the first step of SN1E1 is that we kick out the leaving group, right? But if we did that, we would form this carbocation right here, which is a primary carbocation. And that is not good. We would not form that. That is too unstable to exist. We would not form that primary carbocation. But we can see is that nearby, adjacent to it, is a tertiary position where the carbocation can be stable at. So what we're gonna do is a concerted hydride shift. I'm gonna draw out the invisible hydrogen at that tertiary carbon, do the hydride shift, and kick out the leaving group at the same time to create this tertiary carbocation right away. So that right there, that I just like did, was a concerted hydride shift. Concerted meaning simultaneous, right? We did the hydride shift and kicked out the leaving group at the same time. That's a concerted hydride shift. Whereas the regular hydride shift here, the leaving group left first, formed the carbocation first, which is stable enough to exist, and then we did the regular shift, the regular hydride shift, right there. Any questions on the concerted hydride shift, Kelly? No? Okay, that's good, that's good. No, the other reagents that you talked about, PCC, PBr3, Jones, etc., I'm just gonna put that in a synthesis problem for you to try out, and then I could check that tomorrow in tomorrow's office hours, right? Because I'm gonna go check the 8B problems and the 118B problems here. So 118A synthesis using all those reagents we just did. Like it's gonna have a PCC, PBr3, Jones, organometallic as well. Let me think about this. Let's say we got this barn for your horses, and we got this leaving group, right here. And you want to create this structure right here. Okay, now this is a little baby synthesis. There's gonna be 3 reactions to the synthesis problem for 1-A reaction. Right, so there's gonna be 2 intermediates to convert this starting material to this end material. So let me actually just give you the hints here to help you get started. So one reaction would be this. Another reaction would have first step, second step to get that intermediate, and then the last thing would be something else. Right, so I'm gonna put boxes here in the intermediate for you to fill out as well, because I think this is what Liebens does, which will be what Cagley will probably do as well for 1-A. Okay, that's one for you to try. Let me try and we give you another one here with the other reactions you gotta know. I was gonna do Hornets and V stuff, but you did not learn that yet. I want to do this reaction here somehow, and I am going to give you this, and here are the steps to do so. First, you're gonna do something with a first step and second step to give you your first intermediate, and then you're going to do another step to convert that thing into something, and then you're gonna do something to convert that into this. So this one here has also 3 steps to the synthesis problem. Right, so let's get started with these 3-step synthesis problems for you as homework, Kelly, for tomorrow. Take a screenshot, try it, and I'll check it tomorrow. Okay. Madison, Jenna, have you guys completed the 8B problems I gave you guys earlier?
I think I was able to figure out the first one.
Yeah, let me see. Describe to me the thought process behind it. Like, you could describe to me your product or the mechanism. Either way would work.
So I started with H2SO4, and the oxygen grabs the hydrogen.
Which one?
Oh, the carbonyl.
Yes, that's very important.
Yeah. And then H2O, the oxygen attacks. Okay, well, first we have an OH with a positive charge.
What am I doing? Yes.
Yeah. And then H2O goes and attacks the carbonyl carbon and neutralizes it.
Puffs the bonds with oxygen, neutralizing it. Yes.
And then I think the next step is intramolecular.
Yes. Well, yes, intramolecular acid-base reaction.
Okay. So with the oxygen, what do you call the other oxygen?
You could say oxygen in the ring or the OR group.
Okay, yeah, the OR oxygen would grab the hydrogen on the H2O and then turn that into an OH and neutralize it.
Yes,
Or
because
neutralize it.
we're gonna neutralize this OH, but we're gonna protonate this to get a positive charge. And what we did there was a proton transfer step, which switches the roles of the good leaving groups and bad leaving groups.
Wait, say that again?
So this was a proton transfer step, and we reversed the roles of a good leaving group and bad leaving group. Before this was a good leaving group, now it's a bad leaving group. Yeah. Before this OR group was a bad leaving group, now it's a good leaving group.
Yeah.
Yes.
So now we reform the carbonyl on that OH
Mm-hmm.
and then take out the
Yes.
that yeah.
And this right here is breaking up the ring right here, right?
Yeah.
So to keep track of everything, I numbered it like that, where this is 1, 2, 3, 4, 1, 2, 3, 4, and the 4 is attached to this OH. The 1 is attached to this carbonyl that is positively charged still because it has the hydrogen, and the OH like that. Mm-hmm.
Yeah. The only thing is, if we're kicking out the OH at number 5, why are there two? Wait, hold on. Oh, and then that OH is the one that moves down.
Mm-hmm. This neutral OH here is this right there.
So that arrow only neutralizes it.
It neutralizes it and it breaks open the ring.
Okay.
Right? Like
Okay.
it broke the bond between 1 and 5. There's no more bond between 1 and 5. It's now linear.
Yeah, because we would break the octet rule if we don't break the ring.
Mm-hmm. Yes, yes.
That makes sense.
Uh-huh.
Okay. Yeah, that's what I got.
Yes. One more step here.
Oh, yes. So HSO4 minus is gonna deprotonate that.
Mm-hmm. And make it neutral.
Yep. And then
Yes.
we'll just have oxygen.
Yeah, carboxylic acid, and that was hydrolysis right there because we had acid and water converting this ester into the parent functional group carboxylic acid, right? The leaving group here, OR, is that leaving group right there, but it didn't entirely leave because it's still connected to the molecule because it was a ring like that.
Yeah.
So you could call this intramolecular hydrolysis reaction.
Okay.
Yeah. Madison, any questions on this before we move on to the next one?
No, I almost got it. I just forgot, like, where the second oxygen, like the one on the right, not the carbonyl, but the
OR, this one right here in the ring, part of the ring.
Yeah, that breaks off and becomes an OH.
Yes.
I knew it was one OH, but I forgot about this.
Yeah, this one right here, right? Like
yeah.
Did you create the carboxylic acid though?
Yes.
Like okay, that's good. Yeah, because
I did the top one. I just didn't do the OH on the bottom.
Like on the bottom. Yeah. Right. Because that right there is the tricky part with all the decorations and like the ring and breaking it open. That's the tricky part about this reaction here.
Okay.
Yeah. Let's try the next one.
Sorry. Is a quick way to predict the product for this just to break open that OR group and add two OHs?
Yes. Like you break this bond between the carbonyl carbon and oxygen, right? Because that bond is broken now. And then we put OH. Like this is OH. This becomes that OH right there.
Right? Okay.
And this OH right here of the carboxylic acid came from the water right there. This oxygen of the ring is that oxygen of the product right there. And this carbonyl here in the yellow is that carbonyl right there. So that's like how we got the things right there.
Okay.
Okay. I think we could describe this here. What would happen between this acyl chloride and this neutral amine here?
I was really confused on that one.
So what do you think is gonna happen?
I just know the lone pair is gonna attack the carbonyl carbon.
Yes.
And
it
then,
attacks right away.
Yeah. And then I attach the whole thing.
And the reason why we don't need acid to activate it is because this is the most reactive derivative. So we didn't need to protonate the carbonyl oxygen.
Wait, what was that?
Like in the previous example, we had to activate the carbonyl oxygen by making it positively charged and making it a strong electrophile for the neutral water to attack.
Yeah.
Right? But in this case, we did not have to activate the carbonyl at all.
Okay.
Like the neutral weak nucleophile is able to attack right away because this is already a super strong electrophile. It's already activated. Like because this is an acyl chloride, the most reactive derivative we can have.
Yeah. So with an acyl chloride or the more electrophilic, right?
Electrophilic carbon, yes.
Okay.
Yes, electrophilic carbon, not electronegative, electrophilic.
Yeah. The more electrophilic it is,
Mm-hmm.
You don't need to activate it.
Yes, We don't need to activate it. Now, once we get this to tetrahedral intermediate here, let's reform the carbonyl. And what are we going to kick out?
The Cl.
The Cl. Now, once we do that, we get this intermediate here. But what is going to deprotonate this positively charged nitrogen here?
Is it another equivalent?
Yes, it's the second equivalent of the amine. It cannot be Cl minus because Cl minus is not a strong enough base to deprotonate that nitrogen.
Yeah.
Right there. Right, because nitrogen is like very basic. So we're gonna use another amine to deprotonate. That's why we need two equivalent to convert an acyl chloride to the amide. So that's gonna give us this neutral amide right here, like that.
Oh yay! Okay, cool.
Yes, you got that.
I got the product or the
Yes.
predicted product. I just did the mechanism.
The mechanism, yeah, you got the pattern right. Like we substituted this leaving group with the nucleophile, which is this right here. So that like predicted the product here is very like easy to pick up because we're just substituting this leaving group here with that nucleophile, subtracting one hydrogen right there. Right?
Is it still correct to have the NH on there, like the H hydrogen attached, or no?
If the H is still there, then this nitrogen will have positively charged. That's the intermediate.
Okay.
Right, because nitrogen with 4 bonds is going to be positively charged.
Okay.
That's why we use a second equivalent to deprotonate it and make it neutral.
Okay.
Yeah. Nice.
So
Okay.
just to confirm, after we have the leaving group leave, we take another equivalent and we protonate the hydrogen. Is that or no?
We deprotonate this nitrogen by taking away the hydrogen.
Okay, deprotonate by taking away the hydrogen, and then that would form a neutral
charge on the nitrogen, because when we grab this hydrogen right here, the bond between the hydrogen being grabbed and nitrogen right there, those 2 electrons go onto the nitrogen, giving that nitrogen a pair of electrons and making it neutral.
Okay.
Right, because before it had 0 pairs of electrons and 4 bonds, and when you calculate the formal charge for this nitrogen, it's positively charged. But when we deprotonate it, it's gonna lose a bond and gain a pair of electrons, making it neutral with 3 bonds and a pair of electrons, like that.
Okay.
Right? Yeah. So a lot of 8A stuff, 118A stuff, like comes back as its acid-base mechanism here for sure. Yeah, with the formal charges and everything for mechanism. But you guys get the note card, so that's good.
Yeah.
Yeah.
But we have to worry about a note card and the cheat sheet for the final.
Note card and wait, you guys get both? Like wait, what do you mean? Like note card and cheat sheet?
Like half a page for the final, like half a page front and back.
Half a page front and back.
The note card for the quiz on Friday.
Yeah.
Oh, so a note card this Friday, and then the final next week is half a page front and back.
Yeah, on Monday.
Are you guys gonna copy and paste your previous note cards into that half page?
Low key, yeah.
Oh my gosh, yeah, because there's like no time, huh?
Yeah.
How many quizzes? 5 quizzes?
Yeah.
Oh my god. Well, you guys like those 5 note cards can definitely like the half page will definitely fit more than 5 note cards, so you guys can add more stuff too.
Yeah, that's true.
Yeah.
You gotta like
good.
organize it so it's easy, so you don't spend so much time like.
I know. Like it
everything.
takes a very long time to make very good like cheat sheets, like with like everything and mechanisms. Like I don't know if you saw my 118B and 118C note cards for the iPad one. Like it took me hours to make those ones.
Really?
Yes, it took me hours. I could show you here actually, like the note card. Let me show you my 118C ones. Let me show you my midterm 1, 2, 3. This is for Helix class, and then the dimensions are 3x5, just like Levens, right? But I made 3 copies front and back. Right, like so because this was last year when I made it for my private 2Ts, so they could just print it out and it's color coded and everything, included with all the reactions and mechanisms they need to know for Helix exams, because he provides a study list of what you need to know, and I just like made it very comprehensive as possible, including everything in that list. This is when I had like so much time in my senior year. Like I had like no classes and I just tutored all the time at that corner. Right, like this is the front page right here with all the reactions and mechanisms, and then this is another copy of the front page. But in the back page, when you print it double-sided, like you could cut it out. This is the back page right here.
Uh-huh.
And then I also imported pictures to make it more clear as well. This stuff right here is what you guys are learning right now with like the diagram I showed you earlier, Madison, with the
Oh, yeah.
most reactive derivatives and everything. It's all in there, and I added some extra notes in here as well, just to make it more complete, you know. And all the different reactions. I think you guys learned about ester reactions, hydrolysis. We went over this, right? Basic conditions, acidic conditions, acyl chloride reactions, ester reactions. Where was it? Carboxylic acid synthesis. Yeah, Fischer esterification. Like all the 118C stuff is in here. So this might help you guys out. I can send you guys this as well.
Yeah, I was gonna ask.
Yes,
This
yes.
looks beautiful.
This is the final right here. It's the half page front and back. So this is the front copy, and this is the back page
God.
with all the final material for 118C. Oh my gosh.
Oh my gosh.
Took me hours to make this. Like looking back at it now, like I don't know how I did it. Like oh my
I don't know
gosh.
how you did that.
Dedication.
Yeah.
Yes. Okay.
That's crazy.
Yeah, I'll send it to you guys. I'll send it to
You're
you.
supposed to remember that stuff.
Oh, you remember that stuff? Yeah, like that's why the note card is there for you, because they understand, like you guys just seen this material, so you guys need a note card to understand the material, you know.
Yeah. That's insane.
I think all of you guys have the note card, right? Like 8B leave-ins, 118B helix, and 118A Cagley. Yeah, Cagley also allows note card, so that's good. Yeah. That's so good. Like I don't know if you guys heard, but Nusiri did not allow no card. Mescal did not allow no card. Yeah, like no card. You have to memorize understand the mechanism, all mechanisms of the reaction, and get like write it out when it shows up on the exam.
Oh.
So it was just repetition. Like write out every single step, every single charge for all reactions before the midterm. You know, you can't just rely on your note card.
That's crazy.
Yeah.
Well, thank you so much, Brian. I really appreciate it.
Yeah, of course. I'll send you the note cards for you guys to refer to, and to help you guys make it for your upcoming quiz this week and your final as well, to your guys' for there.
Awesome. Thank you.
Yes, of course.
Have a good night.
Have a good night. Okay, so 118B, Layla and Masna, were you guys able to get this reaction here? Yes. Okay, let's see what you guys got. I think you sent. Okay, let me check. Okay, Layla, you used LDA, create the less sub for kinetic, and then you alkylated the alpha carbon, 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, correct amount of carbons, correct for the first answer. Second one, reacts at the first, but reversible, so it would make the more substituted alkene, which is gonna add the R group to the left carbon, which is more substituted. And let me see if you added the carbons correctly. CH2 ring. Yes, and that is also minus H2. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Yeah, so your major product is correct, but watch out for your minor product ring, right? Like you get the right idea, but when you draw out the things, that's a 5-membered ring. But you got it, Layla. Nice. Yes. Masna, can you describe to me what products you formed so I can check your answer or your work, or you send me a picture of what you got?
Okay. Is it just like first it's like the depronation and then the alkylation?
Yes.
Okay. I think I'll send you a screenshot.
But where you deprotonate for these bases here matters, right? Because you have an irreversible base, LDA, versus a reversible base, turbutoxide. And that is gonna change the regional chemistry of this reaction, like where the negative charge is at, which is gonna affect where the alkyl group ends up at in the major product. And also for 118B, like I made note cards for midterm 1, 2, 3, but I remember that quarter. I did not have time to make the final note card for the half sheet. So I don't have that final note sheet for the 118B final, unfortunately. Let me see. So you LDA deprotonate the less subcarbon 1, 2, 3, 4. 1, 2, 3, 4. Attack 1, 2, 3, 4. Correct. First product. Second product. Yes. Attack that carbon, kick that out. And CH2, CH3. Yes, you got it. You guys both got it correct. Nice. Yes. And this I could see in predict the product or synthesis, right? Because if you see an R group at the less sub alpha carbon, irreversible base, LDA. If you see an R group at the more sub alpha carbon, reversible base, turbutoxide. And then the second step, whatever the R group is, decoration. Okay. Any questions on this problems, guys?
No.
That's good. Okay. Tomorrow, we could go over more 118B stuff. Are you guys on chapter 18 right now for 118B Helix?
Yeah.
How's that? Like, is it overwhelming? Because this is the part where I got overwhelmed in OChem, like the chapter 17, 18's reactions, with all the whole bunch of reactions that are thrown at you. Like, are you guys able to understand the material as he's going on, or is this a lot, huh?
I feel like I'm completely lost on 17, but 18 kind of like brings back to other parts, so I kind of understand it a little more, but I don't know yet.
Yeah, that's good. Did you guys learn about aldol yet? Condensation, aldol dehydration?
Yeah.
Oh my gosh. Okay. What about micro addition? Micro addition?
I don't think so.
Okay.
Yeah, I don't think so.
Because after the aldol condensation, dehydration stuff, there's like 3 more big reactions you gotta know. Micro addition, Robinson annihilation, and then the alpha beta unsaturated carbonyl reactions with the 1,2 addition versus 1,4 addition. Those are the 3 big reactions left in this chapter, in this 118B stuff. So you guys almost done. I can go over it tomorrow, like all those like 3 big reactions, aldol condensation, dehydration, micro addition, Robinson annihilation, and then the alpha beta unsaturated carbonyl reactions tomorrow. Yeah. Okay.
Sounds good. Thank you so much.
Yes, of course, guys. Have a nice night.
Thank you.
Hey, Kelly.
Hi.
Were you able to attempt to use synthesis problems? We could get this out of the way now, or you want to do it tomorrow? Like these synthesis problems here?
I'm looking at it, but I don't know how to think it.
How to think it? Like how to approach it? There's actually
Yeah.
a strategy. Like, have you heard about retrosynthetic analysis or retrosynthesis?
Oh yeah, but I didn't understand it.
Oh shoot. Okay, that is a very important skill that you have to pick up, especially for the end of 118A and like when you get into 118B, retrosynthesis or retrosynthetic analysis.
There was a slide on it, but I didn't get it. And I was like, what's happening? And everyone was like, oh, asking all these questions. I'm like, I'm so lost.
You're so lost. Oh my goodness, Kelly.
I feel bad for everyone I ask questions to.
No, don't feel bad. Don't feel bad. This here is actually gonna take some time to explain. So let's go over this. The first thing in tomorrow's office hours, these synthesis slums and the skill of retrosynthesis and how to think about them. And I'll give you practice after we go over these here. Sound good?
Okay.
Okay. Oh my gosh, Kelly. Did you go lecture today? Did you have OChem lecture or what did you do today?
I had lecture and our professor wasn't feeling well, so she ended 10 minutes early.
Oh, Cagley?
Yeah.
Oh my gosh.
In the middle, she was like, "Guys, I need to sit down for 5 minutes," and it's like perfect 5 minute nap time. I don't know.
Uh-huh.
I feel like I can't pay attention in lecture, and then
You
when I
can't.
rewatch the recording, I can't pay attention to that either. Maybe it's
Oh my
because I don't.
god.
Maybe it's because I don't know what I'm doing. I don't know. But then it's like when I want to ask questions, I'm like, how do I do this? They have to tell me everything from the beginning, and I feel bad.
No, don't feel bad. Like wait, who do you usually ask for help?
I get most of my help on Tuesdays, so I go to TA office hours or professor office hours. But then if I
Mm.
ask everything to professor, then she's gonna be like, "This kid doesn't pay attention to my class." So I don't.
Yeah,
So
and
I'm
then you
like,
feel so bad. You
and
get
then I'm
scared.
like, I don't really want to ask her everything because then it's like, you can tell that I don't pay attention. So then when I asked, everyone's like asking the TA, so then I just listen to them asking the TA, and I'm like, this is not really getting to me. So then I go to AATC after, but then everyone's at AATC.
Oh yeah, it's so crowded there. I heard like recently it's been like so like crowded, especially when I see A people. Like the
Oh,
whole table's
yeah.
packed.
It's
Yeah.
packed, and I'm like, so I need help. And then today someone sat down with me for like 40 minutes, like trying to like help me, and I was like,
Oh,
I
that's
feel
good. That's nice. Like was it packed? Like when they helped you for 40 minutes?
it wasn't like packed, but it was like still crowded.
Oh yeah.
And I was like, what kind of questions am I supposed to be asking? Because I don't know anything.
Yeah, just be honest and let them know. Like, to be honest, I don't know anything. Like, can you teach me from the beginning? And they'll understand and they'll like teach you. You know, well, some
Really?
tutors, they don't like that question. Like I had those questions before, and then I don't mind it, but I've seen others like, tutors like get kind of mad and like and they ask them like other questions and things like that. So it just depends on what tutor you ask for sure.
Yeah, that's what I was a little like uncertain about, because
Mm-hmm.
like since I also teach, I know
Yeah. Oh yeah,
sometimes it's
yeah.
like frustrating.
For sure. Like I know, like if you have to teach everything from scratch, and like it takes a lot of energy and time explaining everything from the beginning, huh?
Oh yeah, and then especially when you're after you explain everything and you're like, please, please, please get like
Uh,
please know it, and then your student goes,
what? You gotta explain
they're like,
everything in a different way. I know, I know.
and then it's like, and then I'm like, oh my gosh, I'm that kid right now.
Teaching requires a lot of patience for sure. Like you understand, right? Like like you
Oh,
teach too.
definitely.
Yeah, I know. That's good.
Yeah, I'm probably gonna end up going to your Saturday
Oh, the Saturday
review.
thing in person?
Yeah.
That's good. That's good. Yeah, I'll see you there in person.
Yeah, am I gonna get my free adjustment?
Yes, you're gonna get a free adjustment. I'm gonna adjust your neck, your back, and you're gonna feel so much better, Kelly. You're gonna breathe so much
Really?
better. You're gonna
Oh,
function so
okay.
much better, and you're gonna like think so much better too. You're gonna like get a better grade because of that too. You know.
Oh wow. Oh, do I need to come early for that?
Um. Yes, come early, or like if like I'm not there by then because I have to drive from San Jose. We
Yeah.
could do it in the break time because there's a break after the 110A review session. So after like during the break time, I could adjust you.
Okay.
Yes, and then it's gonna be great, Kelly. You're gonna like it.
I hope so.
You're gonna feel the big difference.
I told Ali that I go to your office hours now, and he's like, "Oh, you do?" And I was like, "Yeah." And he's like, "Oh, what did he say?" Sometimes I
Well,
ask him for help, and then he's like texting me stuff, and I'm like, I still don't get it. But
oh, yes, I miss him. Ali, like you talk to him at ATC or text?
text.
Oh yeah, that's good.
I think like last year when I first met him, somebody was like, "Oh, are you guys friends?" And I was like, "Yeah." And he was like, "No." And I was like, "Oh, okay, we're not friends."
Oh my God, he's just joking. He's just joking.
No, he had like a pause, and he was like, "Oh." Yeah, the oh moment.
Wait,
And I
who
was
asked
like,
that?
wow.
Who was the person that asked that? That might make a difference. Who asked it?
Oh, I think it was another student.
At AATC?
Yeah.
Maybe. Yeah,
It was in
that
the
makes
residence
sense.
halls.
Yeah.
And
He's trying to
then
keep that professional relationship, you know?
oh yeah, gotta keep the barrier up.
Yes.
But
Mhm.
well, back then I didn't have his contact, and then during finals week I saw him as I was walking to my final from
Yeah.
one final to the next final, and he was
Mhm.
like, "Oh, do you want my contacts?" I was like, "Huh?"
What?
So then I just ended up giving my number anyways, and I was like, "Okay."
Dang. Oh my gosh.
I know. And
Yeah.
then I think he was like, I told him he should come on Saturday and like say hi to you.
Oh yeah?
And he was like, "Oh, maybe if I'm there." And I'm like, "You live in the library. Come on."
Yeah. I asked him last quarter to come too.
Mhm.
But he didn't end up making, so he was probably busy that day. Yeah, so I don't know if he wants to, but thanks for asking him. I tried asking like all the ATC tutors to come last quarter, but only like 2 of them showed up, so I stopped asking the ATC tutors to come.
Aw.
Yeah, I wanted them to come to help out, say hi, take pictures with them, like just for fun.
Mhm.
But not all of them showed up, so it's okay. It's okay. I learned.
He was like, "Maybe if I'm around the
Yeah.
time," like, and I was like, "You live there. Come on.
Yes, I
You're
know.
there all the time.
It's
What do you
our
mean
second
if I'm
home.
there?" It is.
I
Second home
know.
is the 3rd floor of the library.
Yeah, excuses, you know.
Exactly. Like even I will drag myself over there and miss horses.
It's priorities. It's priorities.
Priorities. I got
Yes.
scolded by my friend today.
What happened?
She was like, "You're spending too much time with horses."
Sacrificing the grade.
I know.
Oh
I
my
agreed.
goodness. Yeah.
She was like, "Do you really want to do you really want your DP to drop?" And I was like, She's like, "You don't know what you want." I'm like, "No, I don't." And she was like, "You need to get your head straight." I'm like, "But the horses."
The horses, I know. Oh
They
my
could
gosh.
technically pay for my future rent and whatever.
Mhm.
And she was like, "Be
Yeah.
real."
Be real. Oh my god. But it's the horses. Like I drew out the barn for you too.
Oh
Like,
yeah, the barn.
yeah,
It was
the
a nice looking
circuses.
barn.
Yeah, the cyclopentane, the barn.
Oh yeah, it had like a nice little antenna.
Yes.
The wind, whatever.
The isopropyl antenna.
Yeah.
Oh my goodness.
Very nice.
Yes.
Maybe you should come see the horses.
Yes. Come see the horses. Let's see. When can I do that? Saturday. I'll be there 118A. But can I come after the 118B review sessions? Like after 5:30, or is that too late? Like it's probably too dark by then, huh?
No, you can go, but I just won't be there.
Oh, okay.
Yeah, because I have to run home when I teach my own students.
Oh yeah.
I spent 2 weeks just resting and like doing whatever.
Yeah.
And then they're like, "We kind of want our time back."
Dang. Oh my god. Like, do you sometimes reschedule or let them know that you have finals coming up, exams coming up, and they understand stuff like that too?
They would understand, but I just don't. And I just do it anyways, even with finals or midterms.
Dang, yeah, me too. But
Yeah.
unless it gets very busy and very overwhelming for me, like I need more time unless I'm gonna fail, like or else I'm gonna fail,
Yeah.
Yeah, because I have an exam tomorrow. Tomorrow morning.
Sometimes I'm like, if I don't do their lesson, then I will never get myself out of bed and start working.
Oh yeah. Like it's an accountability thing too. Like tutoring helps you like get your stuff straight and get on top of things for sure. Because if you didn't have that tutoring thing, then like you would be on bed all the time. Like no one relying on you, no responsibility. So
exactly.
Like you won't have anything to get up for. You don't have a reason, But tutoring.
You don't know as time passes.
Yes. You relate, Kelly. Oh my gosh.
Oh, so much.
Yes.
I used to like get up at 5 minutes before tutoring.
Oh my god. Sometimes me too. Because it's online and everything. That's the thing. But then like sometimes I do some I jump around, do some push-ups, wake myself up before the tutoring session, get myself energized because I don't want to be groggy, sleepy during the session, So I gotta make myself.
I just tried to wipe the eye boogers off my face.
Oh my god, Kelly.
And I'm just fumbling around, like sticking my iPad into my computer and all that. I'm like, oh my gosh, when is the Zoom meeting gonna turn on fast enough?
there has definitely been some office hours where I woke up like late, or like I just woke up the minute before and I look so dead like at the beginning of the office hours. Like there's been definitely been some office hour recordings up on YouTube like that.
Oh, really?
It's me, yeah.
Is this conversation gonna go on YouTube too?
I think so, yes.
Oh, fun.
Yes, because at the beginning of the session, I don't know if you could tell, but the beginning of the session I was so dead, like compared to now, like after tutoring sessions, I get more energized. Like I get energy from doing this tutoring, you know?
Oh, yeah. Because your brain is
Yes.
forced to work.
It is, yes, and I have fun talking to people too, you know, connecting with people.
Oh, yeah. Sometimes I kind of let my students just talk.
Yeah.
Because I'm like, I don't really want to teach right now, so they can just talk.
I know. But there's a fine balance for sure, because you don't want to talk for the whole session, or else like, be like,
Oh,
what did I do today?
yeah.
Yes. Okay,
There was
because
a couple times when that happened.
a couple of sessions I have, like, we talked the whole session.
Not the whole session, but like half the session.
Oh my gosh. I'll have to go and
Oh, yeah.
walk my dog now, but I'll let you know about something that you might be interested in, which is like I don't know. I'll let you know more details, like which is the podcast thing. If you're interested, I don't know.
Ooh,
I'll let you know. I'll let you
podcasting.
know.
Okay.
I'll text you. I'll text you after this session.
Okay.
Okay. See you,
Have
Kelly.
fun walking your dog.
Thank you. Have a nice night.